The first Spider-Man move I will be analyzing is his uppercut from the Spider-Man video game. In this, Spider-Man punches the goon straight up into the air. After taking frames from gameplay footage, I took Spider-Man's height in meters, 1.778, and divided it by the number of pixels taken up by Spider-Man on screen, 296. This gave me the number of pixels per meter, 166.4792. By marking the spot of the goon's feet on the ground and his final place in the air, we get a number of pixels which we can then convert back into meters, which is how far he was thrown up into the air by the punch. The goon was thrown 512 pixels into the air, so dividing that by our ratio, we get the height in meters of 3.075. After the goon is no longer in contact with Spider-Man's fist, the only force acting on him is that of gravity. So after rearranging the kinematic formula, distance is equal to velocity times time plus 1/2 acceleration times time squared, we can find that he would take 0.79 seconds to get to the max height. Using the kinematic formula, acceleration is equal to change in velocity over change in time. We can find that the goon would be launched with an initial speed of 7.777 meters per second. Upon further frame analysis, it takes one frame for the goon to reach this speed. At 30 frames per second, we know that one frame is 0.03333 seconds. So, the guy went from 0 meters per second to 7.777 meters per second in 0.03333 seconds. Again, with the kinematic formula, acceleration equals change in velocity over change in time, we can find that his acceleration over this time would be 233 meters per second squared. If we estimate the weight of the goon, a fairly muscular guy, to be 80 kilograms, we can find the force of Spider-Man's punch. Force is equal to the mass times the acceleration, so the force would be a whopping 18,640 newtons, enough to shatter the bones in the jaw, as well as likely breaking the man's neck. If this action took place on a planet with twice the mass of the Earth, it would take the goon 0.56 seconds to reach max height. That would mean he would be launched with an initial speed of 10.98 meters per second. That would change the initial acceleration to 329 meters per second squared, and change the force required to 26,352 newtons. All of this takes place because of the increased force of gravity that comes from an increased mass of a planet. If the action took place in a microgravity environment, the man would not stop moving upwards and therefore would have no max height. This makes the rest of the calculations fall apart, as any amount of force would be capable of launching the goon. Again, looking at some frame-by-frame analysis from the Spider-Man video game, Spider-Man spins this manhole cover one full rotation in 19 frames, which is 0.63 seconds. The length of Spider-Man's web in this shot is 362 pixels, and with another shot of Spider-Man standing up, we can use the scale of his height to find the length of the web in meters. We measure Spider-Man in at 273 pixels. Again, pixels divided by his height in meters, so 273 divided by 1.778 meters gives us 153.5433 pixels per meter. Dividing the length of the web by this ratio gives me the length of the web as 2.36 meters. With that, all we need is the mass of the manhole cover, and we can find the centripetal force creating the circular motion. A typical manhole cover in New York City weighs about 150 kilograms. We can find the velocity of the cover by using the formula. Velocity is equal to twice pi r over the period, to get 23.53 meters per second. Now we have all the values to use the equation for centripetal force. F is equal to mv squared over r. The formula reveals that the centripetal force acting on the manhole cover is 35,190 newtons. This means that the force of tension exerted by the web on the manhole cover is also 35,190 newtons. In this scene, Spider-Man stops a subway train. New York City subway trains typically run at 48 kilometers per hour, and one car weighs 38,600 kilograms. In the scene, we can briefly count 5 train cars for a total mass of 193,000 kilograms.
We're slowing down.
Using the formula kinetic energy is equal to half the mass times the velocity squared, we can calculate that the train has 1.7 times 10 to the 7 joules of kinetic energy. It takes Spider-Man 54 seconds to bring the train to a complete stop. Spider-Man's webs stretch and therefore must be acting as springs, so the elastic force will be modeled by F is equal to k delta x. But for this, we're going to assume a constant force and therefore a constant acceleration. Acceleration can be found using the change in velocity over the change in time, and the acceleration comes out to 0.25 meters per second squared. This can then be used to find the force Spider-Man applies to the train, as force is equal to mass times the acceleration, which comes out to 4.7 times 10 to the 4 newtons. Because the train comes to a complete stop, the work done will be equal to the initial kinetic energy. Using the formula work is equal to force times distance, we can find that the train must have traveled 360 meters. This can be confirmed using the kinematic formula distance is equal to v2 plus v1 over 2 times the time, which also comes out to 360 meters. If the web were an ideal spring, the force would continually increase as the train moved forward, and if Spider-Man kept holding on, would then work to bring the train back in the other direction. In this scene, the Spider-Man villain Electro shoots a bolt of lightning at this railing, and there is a visualization of the current running through. Because this is actual electricity, we can use the left-hand rule to examine the magnetic field that would be induced. Imagine wrapping your left hand around the railing with the thumb pointing to the right, and you can see that the field lines would run into the screen over top of the railing and out of the screen under the railing. In this clip from the Spider-Man video game, Spidey shoots a web at a goon who goes absolutely flying. It is reasonable to assume that the web shot is not very heavy, but as clearly seen, the guy goes really far. Because momentum must be conserved during the collision, the web would have to be moving at an extremely high velocity. Momentum is the product of the mass and velocity of an object, and since the man is likely much heavier than the web and still moves at a high velocity, the web's initial velocity must be crazy high.